Yeah, we'll get back. Somebody was asking to summarize. Okay, the summary here is classical information or classical bits were realized on a magnetic strip by aligning the individual atomic dipole moments along a particular direction, what is shown on the right side of a slide. Okay, so individually what is the atom would look like is shown as the left side. Okay, so all those individual atoms were aligned. So let's say some few moles of atoms are required to store 1 bit of information. That is one of the conclusion we are drawing for classical data storage as a bits 0 and 1. When it comes to quantum, I want to deal at a single atomic level, because at a single atomic level, when I give an electron an energy, it never accepts the energy 100% certainly. Why is that 100% certainly? Because that is a nature for you. Okay, suppose the electron is ground, you supply a photon, which is exactly equal to the separation of this ground and excited state. Okay, electron energy. So that energy may be absorbed or may not be absorbed. Okay, what it means is if electron can exist here or in the ground, both are possible states. Okay, this is possible 60% and this is possible 40%. Okay, now somebody was asking what happens to the photon when it is not observed. Okay, when it is not observed, like some other person is pointing out, the electron is just, sorry, photon just passes away as if there is no atom there to observe its that energy of that photon. It is like system become transparent. Okay, remember, even the existence of the electron at the excited state is in only in microseconds. Even after that, the electron has to come down. When it comes down, it emits that same photon of energy which is taken in the first place, that comes out. Okay, only difference between unaccepted photon and accepted photon to come out is 1 microsecond. Okay, right? Within this microsecond, we have to do the computation. That is the power of quantum computation. We can do a lot of computation. We will see as we go through, right? So if I do a perform experiment, like 60% of the time I see this scenario, 40% of the time I see the next scenario. Okay, so why is because that is because of the nature of the systems at a quantum level or a microscopic level. Okay, so let me give an example to understand this in more detail. Okay, let's say I say a person exists at position A and position B with 60% probability and 40% probability, a person existence. Okay, but it's very difficult to accept for us because we are existing or we are like living in a real classical world where a person can only exist at a particular point with 100% certainty, 100% probability. We can never say I exist in a classroom 60% and in my cabin 40%. It's not the case, right? Okay, but when it comes to the electron, that is possible, because for an electron it behaves like a wave as well along with the material property. Okay, now why that a probabilistic nature actually comes with the wave? Because if you go to a pond, let's say nearest pond is there, like there is a pond or a water body is there, you go and drop a stone into the water body. Okay, right, a water body. What happens? The disturbance is created in between, in the middle. Okay, so because of the disturbance travels outside from the middle. Okay, right? So that is what you see. So disturbance is created at one point, it travels outwards. Now if I ask a question to you, where is that wave located? The wave which I created at some point, where is that wave located? You would simply say wave exists everywhere. Wave exists everywhere. Even though I created disturbance at single point, it exists everywhere. Let's say we see the ripple traveling out in circles. Okay, right? So the wave exists everywhere. It is not contained in one point. So a wave associated with anything would exist everywhere. Now, if I have a electron associated with some wave nature, its existence is described by its wave nature. What is that wave nature is? Let's say its wave nature would look like this. Okay, fine, something like that. So there is a probability associated with some the hill, it's and another probability associated with another hill of a wave, and wherever the wave is zero, right, there is no chance of existence of the electron there. Okay, so this is a crude way of saying, which is slightly confusing. Let's take, if I just take a box, okay, and put an electron inside a box, particle in a box, people call in quantum physics. Okay, now the electron is there inside a box. I'm not supplying any energy, but still it can move here and there. Because of that, it can have a de Broglie wave nature, de Broglie wavelength associated with its wave nature. Because of that, what happens? Electron exists in the wave form. Wait a minute. Okay, maybe we should start a new one, so it will take a lot of time. So it's loading up all the text we have written earlier. Okay, so let me take a new one. Okay, so now the electron inside a box, okay, electron, right, that electron inside a box would get associated with the wave, not a single type of a wave. It can get associated with multiple waves. Okay, what is that multiple waves is? There may be a wave nature where only one wavelength is confined in that box. There may be a wave nature, there are two or one and a half wavelength confined in it. There may be a wave nature, two wavelengths get confined in it. Okay, so two wavelengths, one and a half, one wavelength. Okay, so like let's say this is a this is a kind of a let's say some x1 kind of a wave, x2 kind of a wave, x3 kind of a wave. So electron can exist in a box with multiple states. Okay, so what is the chance of it exist like this? What is the chance of it exist like this? X2, x3? It is all probabilistic in nature. And more than that, let's say it exists with this nature. And what is the chance of its location? So what I can do, take the wave nature of the electron. Let's say this time, let me use that a Greek letter psi1 instead of x1. Take the absolute square of that wave nature. Okay, so just plot it. What you see is like this. Okay, what it means is, let's say the box length is 0 to L, one dimensional box, 0 to L. Wherever the wave nature is peaking, there the chances of electron finding is maximum. Wherever the absolute square is going to 0, no electron there, and there is a maximum electron. So what I mean is, I take the wave nature of the electron and find its location, possible locations of the electron. It's a very, very interesting thing. Okay, so because of this, what I see, an electron can exist here or here, not exist here, no existence. Okay, so like more. Okay. In that way, I can choose to electron to exist in this Z. Let's say this is Z, and this is called E, excited state. Okay, so this is how electron is not going to be settled in a particular state. It is going to probabilistic in nature because of the duality. The dual comes when things are so tiny, things are so fast, then the wave nature get associated. Now as I go to larger, let's say bullet and cricket ball and a football and let's say a moving car, there is no wave nature associated. Even though there is a wave nature, the wavelength of that wave nature is so small, I can't say there is measurable. Okay, remember, you can give a bold statement, everything in the universe has a wave nature. Even we have a wave nature. People say there is a sign, we can see the aura behind it. Okay, so they write, like they draw circles behind his head. That is what we see, the representing a science. Okay, what they mean is there is a wave aura around him. Okay, but when in a classical world, a real world, a macroscopic world, the wavelength of that wave nature is so small, I can't measure it. 10 to the power of minus 40 compared to 10 to the power of minus 15 or minus 10 optical wavelengths. Okay, or the visible light range. Okay, nanometers. Fine. So because of that, I can simply say, use this ability of the electron to exist in multiple places with probability to realize a memory. Okay, so this is what I just draw, a wave function. A wave nature is described by a mathematical function. It's called a wave function. What you see on the left, you take absolute square of it, you will get possible wave locations of the electron. Okay, I just did this for one dimension. If you do this same thing for a 3 dimension, don't get alarmed by this. This is the Schrodinger equation in 3 dimension. Okay, it's a differential equation in space. Okay, at particular time t, and if I solve this differential equation and find what are the possible, see here, wherever there is a hill, there is a possible location of the electron. Okay, now this is a ground state, excited state, second excited state. N equal to 3 is second excited state. Now, if I solve that for a 3-dimensional system, let's say hydrogen atom, okay, for a nitrogen atom, if you say see what are the possible locations or maximum probability locations for an electron around the nucleus, if you see, there are so many dots. Even though the single electron is there, there's so many possible locations. Okay, right? As you go away from the nucleus, number of points decreases smaller and smaller. Okay, right? Fine. And there is one more factor also. So at quantum level, I can't specify its location and velocity with precise, because things are moving very fast. Either I can choose velocity to specify exactly or choose to specify location exactly. Because when I specify location exactly, means I am compromising in specifying velocity. That is uncertainty for you. That also comes because of this wave nature at quantum level. So they have like Heisenberg has put it up into the equation to represent that behavior as saying, whenever I try to measure a position of an object and a momentum of an object at quantum level, a very tiny scale, I'll always make a mistake of an error of delta x and delta p if I multiply that error, which is always larger than the Planck's constant. That is what h cut divided by 2 show. The same equation also I can describe in another way. If I try to find what is the kinetic energy of a moving particle, okay, how long it exists with that kinetic energy, if I try to find the time period, I will also make some mistake. What is that mistake is, I'll make a mistake in finding the exact energy by delta E amount of error and time period with delta T amount of error. You combine and product that, you would always come up with a number which is larger than Planck's constant. That is uncertainty for you. Okay, fine. Now, people thought, can't we use that uncertainty or probabilistic nature to realize a memory out of it? That is a quantum memory out of it. Can we do that? Of course, yes. What is the technique is very simple. Okay, take an atom, send a photon to the atom. The atom energy, the photon energy is which is close to the particular two orbits. Okay, right? Now, as we perform that, okay, so there is a ground state, there is a ignited state, there is a photon coming in. Okay, now there is a probability of 60%, sorry, 60% excitation, 40% not excitation. These are numbers, you know, these are two numbers. Okay, so I would say these two numbers would exist for 1 microsecond for a given atom. If I send a pulse of 100 photons, okay, and keep observing the system, okay, in this 1 microsecond, I would see for 60 times electron being excited, 40 times electron not being excited. Okay, so that is a probability for you. Those using those probabilities, I can store two numbers on it. 0.6 probability, 0.4 probability. Okay, I can store. How? Again, I can use the wave nature as a means. In a wave nature, okay, wave nature, if I just take, and if I take a wave associated with a particular system, take absolute square, it gives me the probability of maximum location, probability of zero location of that particular object. Okay, so that is how I can associate a wave nature, let's say n equal to 2, and no wave nature for n equal to 0. In that way, okay, or n equal to 2, I'll have a maximum, n equal to 1, I have a minimum, right, of a wave. In that way, I can have the more existence of electron at the excited, no excitation, no electron at the ground. And this will happen flipping continuously because I send a stream of photons and this will go up and down. It is just like a fan rotating continuously. Okay, right? So people thought, why can't we realize a memory out of it? So they take that numbers of probability to realize a memory. Okay, so that is the idea. I can store two numbers on a given atom in the form of their probabilities. So how it is done? Okay, let me show you. Okay, so they call it a superposition state because electron could exist in both the places with some probability. It's like collection. They call it a superposition. Now let me write down that superposition state into a mathematical form. Okay, so how do I do? Let me write a Greek letter psi. I want to connect to a wave function, so I wrote it a wave function. Psi is equal to 40% not excited plus 60% excited. Let me write down that way. Okay, now the idea was to make sense. So 40 plus 60 is 100%. Okay, very good. I confined to only two orbits. Okay, now if I say this mathematical function psi is a wave function, it is an absurd statement. Because why? What is a wave function for me? It is a sinusoidal wave, a sinusoidal function, which should look like psi is equal to some cos k into x minus omega t. Okay, that is a wave function usually. Means if I create a disturbance along the thread, that is a sinusoidal disturbance, right? So it is a sinusoidal function like cos or sine function. Okay, where k is a propagation vector which is connected to lambda wavelength minus omega t, where omega is angular frequency with frequency which at a given point the vibrations can happen. Okay, right? So this is a wave function, but what I wrote in terms of probability sum or probability 40%, 60% thumb, it is not making sense. Mathematically, it is not making sense, right? Why it is not making sense? Because if I just take psi, which is written as a cos absolute square, I get a nice hill, which is close to what I saw in the case of an electron in a box. But what I wrote now is not making sense. 40%, 60% sum is not making sense. So Dirac, a scientist by Dirac, a physicist, he saw this. Can we bring some sense into this? Okay. How to bring sense into this is, let's say I will not sum the probabilities 40, 60 as it is. I will bring something called probability amplitude. Okay. So why probability amplitude means you go back and see electromagnetic wave which is traveling. Okay. Traveling electromagnetic wave. This is the amplitude of the wave E naught. Okay. You take absolute square of the E naught. Okay. Okay. Absolute square E naught. What you get is you are going to get the strength of that particular wave. Okay. So you get absolute square, you get the strength. Similarly, like Dirac thought, instead of saying 60% as it is, let me say that as alpha square, where alpha is probability amplitude. Okay, and alpha square is probability. Okay, this is simply like electromagnetic wave. E naught is amplitude of the wave, and E naught square is the strength of the wave. Okay, he took that idea and he used it. Now what happens, instead of writing psi as 60 excited plus 40 not excited, okay, he introduced a new way of writing in the form of, let's say, alpha times excited plus beta times not excited. Okay, right? Now see, the word excited and not excited is there. That's a state. Okay, so he just introduced a notation to represent a state by just saying a vertical line and a right angle, vertical line and the right angle. Okay, I'll come back. Why is that direction? Like on the left hand side also introduce vertical line and the right angle. Okay, like why he introduced this vertical line and the right angle is actually a part of the idea of bracket. Okay, so right side he introduced the right angle side, the left side introduced the left angle, so together it becomes a bracket. Okay, so there is a vertical line, there is a vertical line. So he introduced this notation. As of now, this is the notation. Now it is, he said, it is just like a equation of a straight line or a line which is looking like this. Okay, so equation of a line, xi plus yj, a two-dimensional line, equation of a two-dimensional line, right? If you do that, there is a, see, this two-dimensional line is what? We just take a x and y axis. Any point on the x and y axis is r having x component, having y component, and r is this. And he said this quantum state of an electron being excited or not is, I'm writing like a equation of a straight line, a vector. Okay, right, where this excited state, not excited state, they are like a base elements like I and j. Okay, so instead of writing excited and not excited, he just wrote 0 and 1. Okay, so some people use 0 for excited, 1 for not excited. You can do other way around. You have to stick throughout. So for time being, I said psi is equal to, okay, let me, sometimes I write arrow mark. Okay, so 0 beta 1. Okay, so wherever I have used a right angle, I call it as a kets. So I call psi ket is equal to alpha 0 ket plus beta 1 ket. Okay, so just he introduced this notation to bring a sense into the mathematical form he's writing. Now you take a vector r xi plus yj. Okay, right? Now you take absolute square of the vector, means the length of the vector, which is simply x square plus y square. Okay, right? Similarly here, you just take absolute square of this vector. I can say alpha square plus beta square, right? Alpha square plus beta square, which is just similar to x square plus y square. In this particular case, what we see, alphas are alpha square and beta square summing to 100% probability, or it is equal to 1 probability 1. Okay, right? So in this way, he brought sense into the equation of writing a wave as a Ketz and brass. So what is a bra for you? Bra is a left angle and a vertical line. Now, this is a 2D version, like description I was doing. So what he did, he just compared the base elements of two-dimensional vector space I and J to the 0 ket and 1 ket. Okay, but in the two-dimensional vector system, if you confine x square plus y square is equal to 1. Okay, so what you are talking is, you are talking about points on a unit circle. Okay, where r equal to 1. So all the points on the unit circle only we are talking in this situation, right? This is a quantum system which we taking, it is just like that. Points on a surface where the surface is having equal distance from some orbit, so some center point. We'll come to that. What is that? Okay. Now, so he did that, and he saw there is a very good resemblance between the base element of I and J with 0 and 1 if you introduce that matrix interpretation. What is that matrix interpretation is? If you introduce 0 ket is equivalent to a column matrix 1 0 and 1 ket is equivalent to 0 and 1. If you introduce this, if you want to multiply 0 with 0, since dimensions are 2 by 1, 2 by 1 here, I can't multiply. So I can't multiply same dimension things. So I have to, left hand side, I have to take a transpose. What is that is? Left, the ket becomes a bray and right side remains the same, which is equal to 1 0 1 0, which is what? Beautiful. So 0 with 0 gives 1, 0 with 1 gives 0, 1 with 1 gives 1. So he said, I can introduce a matrix interpretation of 0 writing as a column vector 1 0, 1 writing as a 0 1 column vector, and if I introduce that matrix multiplication with the catch, left hand side entries are taken a transpose and then did the multiplication. Whenever I write x comma y, I'm taking a product of two elements which is equal to take a transpose of the left side and multiply to the right, which gives me something. That is the matrix interpreted multiplication he has introduced in this case. So ket x, ket y becomes like this. Okay, right? So if I introduce that, it all makes sense. And what is that sense is 0 ket and 1 ket would become a basis equivalent to I cap and J cap in two-dimensional system. Okay, where x absolute square plus y square is a unit circle, and here alpha square plus beta square is equal to 1. That is a probability 1. Okay, so this is a constraint. All the quantum states, by the way, is having unit length Okay, so this is a unit length, unit vector, and also quantum states are always having unit length. Okay, right? So that is the interpretation. And also he, like, later on a Bloch sphere was introduced. What is that Bloch sphere is? See, the unit circle is this. Any point in the unit circle is geometrically interpreted a unit vector. Okay, is there a geometrical interpretation for my quantum state? I can use this, but I can't use the alpha probability amplitudes on the unit circle. So what they introduced, an interesting idea they introduced, they took an idea of spherical coordinate system. What is a spherical coordinate system is? Spherical coordinate system will have r cap, theta cap, and phi cap, 3 dimensions. Okay, I can also write I cap, j cap, and 3k cap in Cartesian coordinate system. Cartesian coordinate system. This is spherical coordinate system, 3D spherical coordinate system. Okay, so they said, let me use the idea, some information from spherical coordinate system, write the quantum state as cos theta by 2, 0 ket, plus sine theta by 2, exponential I phi 1 ket. Okay, since I don't need a third dimension of spherical coordinate system, because length of my vector is not going to increase or decrease anything other than 1, so I just disregard the dimension of r. I just use the dimension of theta cap on phi cap. So what I get is, I get a surface of three-dimensional surface. So three-dimensional spherical coordinate system. Okay, the surface, whatever surface you see, that is going to represent a quantum state. Okay, if you fix theta equal to, let's say theta equal to 0, what is the theta, by the way? Theta is, in a spherical coordinate system, theta is the angle between z axis and the vector r. If theta equal to 0 means what? Psi is equal to 0 ket. And theta equal to 0, theta equal to 0, this is not going to contribute. No? So a north pole of a Bloch sphere would represent a 0 ket, and if theta equal to pi, which gives me sine theta by 2 equal to 1, which means quantum state is going to be equal to 1, means south pole of a Bloch sphere is a quantum state ket 1. Anything other than any other points, if you take, they are going to be a combination of all the thetas and phis. So any point other than north pole and south pole would represent a possible quantum states. Okay, so that is a geometrical interpretation for you. Now I'm not going to confine myself to just one qubit. Means the information stored as 2 bits on an atom or an electron is a qubit for you. It is called short form quantum bit, a qubit. Okay, so mathematically I represent a qubit by a matrix notation of 0 ket and 1 ket used as a base vectors, and I create a vector, quantum vector psi, with the probability amplitudes alpha and beta, where alpha specifies probability of alpha square specifies probability of system being excited, and beta square says system being not excited. Okay, now the question is, am I only dealing with the 2 bits of number? No, I have to deal with large number of bits. So how can I create large number of bits or quantum bits? Is simply take 2 atoms or 2 electrons, bring it together. Okay, when I bring it together, okay, let's say it's like taking a 2 coins, toss together. When you toss together, right? So if you see, what is the chances of the results? Both the coins are tail, both the coins are head. First coin is head, second coin is tail. First coin is tail, second coin is head. 4 possibilities. Similarly, if I take 2 atoms, put them together, what is the chance of the electron to exist in the ground or excited in both the atoms? Is the first one is in the ground, second one is excited. First one is in the excited, second one like this. Okay, so the moment I bring in two atoms together, I have a chance to create 4 possible information storage. Why? Because let's say there is a quantum state of an atom is alpha A 0 ket, beta A 1 ket. Second atom is alpha B 0 ket, beta AB 1 ket. If I bring them together, I'll have 4 numbers, 4 probabilistic numbers. Those numbers would be like alpha A, alpha B, alpha A, beta A, something like that. The combinations I will get. So literally I'm going to create a higher dimensional quantum system where base vectors are 0, 0, 0, 1, 1, 0, 1, 1. Okay, you can follow the same strategy and create. Okay, you see this is a short form like written for a 2-dimensional quantum system where the column matrix representation for 0, 0 is 1, 0, 0, 0. Okay, now the question is, how did I get that kind of a multiplication? I don't see matrix multiplication like that, right? It is called tensor product. What is that is, if I want to multiply two vectors of same dimension in a tensor product, what you do is take the first element, multiply it to the elements of the second entries. Similarly, you can derive. Okay, so this whatever this strategy I have here, that is showed in the next slide. Okay, right? So I can follow this. I can continue to generate large dimensional system. Take two atoms together. Okay, two atoms creating 4 memory. Okay, which is equal to the power of 2. 3 atoms, 8 memory locations, which is 2 to the power of 3. If I keep going, if I just take n atoms, what is that? 2 to the power of n memory locations are generated. Okay, if I just take n equal to 50, 2 to the power of 50 is so large, I can do lots and lots of information processing and storage. That is how the quantum memory is going to outplay the classical memory with just a storage. Okay, and one more beautiful thing here is this memory is so like sensitive, it's hyperactive. There is absolutely no delay in storing the information and retrieving the information. Okay, right? Fine. So let me get back. Okay, the gates. We'll come to gates as a part of, I think, next session. So let me go over it. The gates, there is a C0 gate. This we'll discuss in the next session. Okay. All right. I want to talk these things. Okay. Now the question is, just the electron being excited or not excited, is that the only way I can realize a qubit? Of course not. There are so many other ways I can realize a qubit. Okay. What is that ways? Right? If you just take an electron itself, electron which is revolving about the nucleus, okay, right? It is, okay, wait a minute. Hello, can you hear me? Hello? Yeah, somebody just point out. Are you able to hear me? Yes, okay, thank you. Okay. Right. So electron, instead of just rotating about the nucleus, it is also rotating about itself, just like Earth rotating about its own axis. So it is rotating about its own axis. Okay. Right. Electron rotating about the nucleus creates a spin rotational angular momentum. Okay. So which is actually equal to half h. Right? So it can rotate in counterclockwise or anti-counterclockwise, so that it has a spin plus or minus half h, or spin or magnetic moment, spin magnetic moment they call. Okay, or rotational magnetic moment, I'm sorry, rotational magnetic moment, and it is rotating about itself also, so it constitutes a magnetic moment like this. Okay, so that means the electron, instead of just going around in the orbit, it also does the dynamics of rotational dynamics. Because of that, it creates a spin a magnetic moment. Now, is it certain? Of course not. The spin is also not certain because it is a tiny thing. So sometimes it is up spin, sometimes it is down spin. It is a plus half h or minus half h. If I take an electron and try to observe, make observations, 60 times it is like this, 40 times it is like this. Okay, that is also probabilistic in nature. So I can take a spin of an electron itself as a means to realize a qubit. Okay, or the rotation about the electron about the orbit as a means to realize a qubit. Okay, so that is what I was showing. And one more thing, we keep forgetting, even the nucleus is so big, it can also rotate about itself. It also constitute a magnetic moment, spin magnetic moment. So that also again not certain, it is a probabilistic. So that is what you can use a nuclear spin or electron spin to realize a magnetic moment. And now there is something called ion trap. What is ion trap is, if you just take atoms like barium, okay, or there are certain periodic atoms in a periodic table, they're very, very interesting atoms. Okay, so what they do is they're suited for this quantum qubit nature. Okay, so you just remove an electron from that, they become a positive ions. Okay, and these positive ions can exist in two states or multiple states. So what is that multiple states is, there's so many states are there, just like an atom. The ion can exist in multiple states. I can choose any two of them and create a qubit out of it. Okay, so some of the examples of light as beryllium and magnesium, calcium, okay, strontium and ytterbium. These atoms are there. You knock the atom or add the atom into it, they're going to exist in two states, which is a ground state and an excited state. I can use a qubit and create a qubit out of it. Okay, right? So that is a ion trap for you. And the thing is, since they're positively charged, let's say beryllium, I remove one of the atom, one electron, it becomes a positive ion. I can just take electric field plates and confine that beryllium within that. Okay, let's say it is confined in a horizontal direction, so it moves up and down. Let's say I just put a laser light. Laser is nothing but electromagnetic wave, na? It has electric field also, so I can constrain to not to move in this direction. Okay, equal forces are created in all the direction. It is confined to a particular location, and when it is confined, it exists in two states. Those two states I can use to create a qubit out of it. That is ion trap for you. Okay, right? Electron spin, nuclear spin, straight away we know that the spin exists either up spin or a down spin, plus half or a minus half. Okay, right? So that is the one thing. And if you just take materials like semiconductors, gallium arsenide or anything, if you take it's like a semiconductor material, right? Okay, you take a host, remove some insulators and put some conducting, it becomes a semiconductor. Okay, right? So if you take that, within that semiconductor, I can club few electrons and confine the electrons into a certain location, and those electrons may exist in multiple states with some probability. They may have various charged states, or like say plus 10 or minus 10, like that, or they can, their spin can exist in, let's say, some certain magnetic moment of 20 magnetic moment or a minus 10 magnetic moment, something like that. They exist in multiple states. That also I can realize a qubit out of it. That is a quantum dot, or confining the electron in a particular location. That is a quantum dot for you. Okay, so both the electron in a rm or electron in gallium arsenide or a quantum dot, all the three things belong to the same nature, that is confining the set of electrons into a particular location. So in the first two, only one electron I was talking. In the case of quantum dot, I take a collection of electrons confined to a particular region. That gives me a qubit out of it. Okay, right. Another one is, let's say take photon itself. Let's say I have a mirrors, a curved mirrors. If I just put a photon, ensure that photon goes back and forth. Okay, right? And when we make a small hole, it is the photon will come out. So I'll send a stream of photons. Okay. When I start studying the output, what I see, output which is coming, which is in streams, like different frequencies. Okay. So as if they know how many number of rounds they have to make particular photon. So at a given point, if you see, there are different kind of states exist in the photon rotations inside an optical cavity. It's called optical cavity. Okay, right? If I take any single photon, what is the chances of it is making 10 rounds or 20 rounds? It is probabilistic in nature. So that also allows me to create a qubit out of it from an optical cavity. So that is what showed here. Optical cavity also very good means to create a qubit out of it. Okay, so microwave cavity, I use the radio frequencies inside a microwave. So there I will create a qubit out of it. Okay, so this is how I create a qubit. So there is a question, there are so many ways I can create a qubit. What is the best? Which method I should choose? The question is like answered by the next three columns you see. So there is something called a decoherence time, means how many seconds the system would behave as per my wish, means it is existing in an excited lifetime. Or if I take certain qubits behave the same way for some time, like say dancers, 10 dancers on a stage behaving the same way with synchronicity, that is coherence for you, that is a coherence lifetime. Okay, how many like for each operation to do on a certain system, how much time it takes, that is given in a second column. Okay, so if I divide first column by second column, I'll get number of operations I can do. If you see, the number of operations I can do in each case is of different order. So we usually greedy, we say nuclear spin is a very good means we can realize a large number of quantum operations. I can, let's say I can devise a quantum computer out of it. It's not that. Okay, so we have to strike a balance in control and sensitivity of the system also. The nuclear spin systems are very vulnerable to external means. Okay, so that's why even though the number of operations is offers a lot, people choose different methods. People choose, let's say, ion trap. Okay, people choose optical cavity or photon based systems. Okay, so this is how now I have a simple pictorial diagrams here. What you see on the left hand side is left side at the top, it is a superconducting based quantum chip where 4 qubits are realized. On the right side top, you see photon based quantum chip. On the bottom left, you see ion trap with electrodes. Okay. On the right, you see there is a NV center cavity they call. We will touch somewhere in the sessions. So it's NV center means you take a diamond, remove the carbons, and put one nitrogen. Interestingly, this nitrogen couples with the vacant space of a carbon, creates a nitrogen vacancy. It becomes a dipole. This dipole behaves in two ways with the quantum state. So that becomes a qubit for you. Okay. So these are like, this is different ways of realizing a quantum qubits. Okay. Now, I was not give you the description of what is this superconducting qubits is. It is just a simple LCR circuit. Okay, just take a LCR circuit on the right side corner. What you see, the LCR circuit, the inductor is there, capacitor is there, internal resistance is there. You connect to output, oscillating output, input. So you get, what you get is the capacitor being charged in various stages, like say 5 coulomb, 10 coulomb, 50 coulomb, 25 coulomb. So capacitor can exist in a fixed charge state, 5, 10, like that. So like capacitor can be used to realize a qubit using taking only 2 states. But thing is, if I choose any 2 of them, I might get a chance, like I will be having a chance where the information is leaked to some other state, because every 2 states are equally separated. Okay, so what people thought, okay, let me remove an inductor, put in place of inductor a sandwich of a superconductor and an insulator. So that they call it as Josephson junction. Interestingly, this Josephson junction acts like an inductor because the superconducting left hand side induces some effect on the right hand side, and right hand side induces some effect. It's like induction. Okay, so if you take this Josephson junction, put it in place of a conventional inductor, the separation of the charge states of a capacitor becomes unequal. That in that way, I can ensure that my quantum information is only stored in two particular states, not all other states possible. Okay, so this is how people realize artificial atoms. You see, the energies like a capacitor charge separations is non-linear, means not equal. Similarly, on the left-hand top, I have a real-world atom, or classical atom, sorry, a real atom, where the states are unequally spaced. So this is how people started using artificial atoms to realize the qubits. Okay, right? So that is what we wanted to cover. So we covered it briefly. So we go into the details as we go further and further. Okay, right? So in the next session, that is on Monday, Professor Dr. Anindita would give what is a quantum advantage we are actually seeing these days, what we can expect in future, that she will cover. In the later half, I will start with the quantum gates. Okay, so this PPT is already shared. Okay, I'll share my hand notes also, whatever scribbling I did. So you can just follow through it. But if you read through my lecture notes, you would understand what I mean. Okay, so I urge you people to go and cross check how single qubits are realized, mathematically how to represent them. Okay, how higher dimensional quantum qubits are realized with a tensor product, how it is mathematically represented. Okay, so those 3 to 4 slides, like slide number 21, 20, and 19, and 18, and 17, please check and understand. Okay, right? So I'll stop giving lecture now. If there is any questions, I will take. Oh yeah, Prasanna Kulkarni saying this is very elementary, sir. Maybe skipping. Oh yeah, for some of you people, yes, I understand it is elementary. Maybe there are people who are new to the field. For them, we have to cover, right? Okay. So I'm sorry if it is redundance repetition for you. Please bear with us. We will go to the advanced stuff as we progress through. Since we have to cover from the very much fundamental to advanced systematically. Okay. If it's uncertain, then how can the electron be contained, and is there any source required for the continuous containment? If not, data concurrency problem might occur in case of computation. Right. So in the case of computation, I'm not going to use the scenario of certainty. I am going to use the scenario of probabilities. I am going to use the probabilities of alpha square and beta square to do the computation. Okay, I'm not relying on the certainty there. I'm relying on the uncertainty. I'm going to create my storage based on the probability. That is how I'm doing the computation. Doesn't matter. Let it be uncertain. Let's use that uncertainty as a positive thing. That is how quantum memory is being realized. Okay. Right. So okay. Can we? Okay. Let me see from the back. Is there questions? Okay, let me see from here. It is a bit complex to understand as I don't have prior knowledge of quantum, but your sessions are great for newcomers. So thank you. Krati, yeah. Multiple states in a wave, particles for a quantum. Yeah. See, everything which is ambiguous, not certain, is a means for me. The closest one I can think of for describing a quantum nature, it should not be used, but you can do. For example, you just take a fan wings. When you switch on, it appears that wings are everywhere. Okay, when you just poke a stick, it stops abruptly at some point. Okay, it is not quantum in, by the way, it's a macroscopic object, but that is the closest thing you can take. Other one is toss a coin. During the flight, if you see that coin is in head and tail position. So that is a means for me to realize, express the quantumness. Okay, right? Okay, so Questions. If for first method, by increasing the number of photons, can we increase the electron excitement probability? Yeah, it's a very good question. it's a photoelectric effect. That is actually the main thing which led to the birth of quantum physics. The notion of adding more photons is not going to guarantee putting the electron to excited state. No, because unless there is a match between the separation of the energy with the incoming photon energy, then only there is a chance the electron could jump. Doesn't matter, unmatching photons you send like thousands, it's not going to do. Doesn't matter you send 1,000 photons of this equal energy, all will ensure that they push to the excited. That is not going to. The electron would take either one photon or doesn't matter. If it decides to not take, doesn't matter. Okay. So, yeah. Right. So, particle duality, very important to understand with a different state. Yeah. So, just like electron behaving like a particle as well as wave, similarly, photon behaves like a wave as well as particle. So, photon can also become a wave of a particle. How? There are experiments which were shown. They are taken a thin foil, shine a photons, and go and do a head-on collisions, and they transfer their momentum to this atoms on the thin foil. So they're like it's like a billiard balls on our carom coins. So that is how people experimentally seen photons being a particle in nature. Okay, right? Yeah, would you suggest any book for the content? I would suggest Nielsen and Chuang, Quantum Information Science Confirmatory Theory book. Nielsen and Chuang, it is available on the net. You can download and you can study. That's a very good book. People call it a Bible for quantum computing. So you can follow that. Okay. So any other question? Does photon have a mass? Photon have a momentum, linear momentum, but I can't associate a mass. Okay, right? It does behave like a particle by hitting and transferring its momentum to that hit, like head-on collision, the particle, whichever it is collided. Okay, so I can get a mass equivalent calculation. I can do that, but I cannot say exact mass it has because it's an energy, na? Right? E equal to mc square connects energy to the mass. Einstein's greatest equation. So energy can get converted to matter, matter can convert it to energy. So same way, photon can show the material behavior, but it may not have exact mass of a material. Okay. So, okay. So many doubts. For the past 15 years, I have been teaching EMTL, but I have not been thinking in this context. Now I have got more ideas to teach in quantum domain. Thank you so much. Okay, great. Hard to correlate everything together for complete understanding. Yeah, but don't worry. Actually, see, this is how things are. Quantum physics. When people are designing quantum physics, after designing quantum physics, people like Einstein themselves had a tough time to accept and tough time to agree because it is against our intuition. When I say something is not there on table and exists on a table with probability, it's difficult to accept. But it is the way it is at quantum level. So when you are saying you're not understanding quantum physics, means you are really understanding. Okay. 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 Yeah. Okay, there's a long message. In the following understanding, is it correct? I think they're asking. Psi A naught, okay, is equal to. Yeah, I think fine. I think superposition. If superposition X, okay. We'll talk as we go much in detail later. Very good. I think there is a good question here. I think Lalit was asking. Higher dimensional systems are typically visualized. Qubits are on a Bloch sphere visualized, but when it comes to higher dimensional system, it has four bits, right? Four basis states. So it is not possible. So IBM has come up with something called Q-sphere. It can go up to 5 qubits. It can show 5 or 6 at the most. I'll show you sometime. IBM quantum experience graphical interface. Okay, it is very difficult to depict geometrically the higher dimensional quantum system. Only we can write on in the form of mathematical equation, in the form of tensor products. Okay. How can we control these qubits accurately? I've asked many times, but even time it is kept. Qubits are accurately. So how they are, like, depends on the type of quantum qubits which we chose. Artificial atoms like the ones which I showed. This one, the leftmost. Okay, the chip is cooled to millikelvin so that the qubits behaves as per the requirement. On the right side, photon-based quantum chip. Okay, maybe cooling is not required as much as superconducting based. Okay, they ensure that only certain number of photons are involved. Okay, and even for the same, the cooling is done for ion traps. And interestingly, for NV center based quantum computing, cooling is not required because they are existing within a host. Okay, they are only sensitive to the surrounding environment. Okay, right? And they don't need cooling. They can exist in a rigid qubit quantum state, even they're in the room temperature. That's why it is taking a precedence, the NV center based quantum computing. So it's picking up for the magnification, for the medical application. People are exploring it. Okay, fine. So let me see a few more questions and I can stop here. Any other questions? De Broglie hypothesis. Yeah, that is what de Broglie wavelength, what we had. Okay, so yeah, you guys have my number. Qubits are dual in nature. Yeah, qubit means quantum, so it is already existing in quantum nature. It can become a classical. Okay, when you try to observe it, that becomes so fragile. Okay. Okay. Fine. I will stop at this point. So we should also not take too much time of our organizers. So Satyendra sir, please take over.
Yes, sir. Thank you so much for today's session, and we will participants. We will have the next session on Monday, I think.
Yeah, I'm sorry if I had taken extra time also.
No, sir. Thank you so much for this wonderful session. And PPTs are PPTs are already available in the Canvas. Please log into Canvas. If you have any issue regarding the Canvas, we had a session today at 12 p.m. And we had recorded that session. You can see that session. We'll post the link in the. We have already posted the link in the WhatsApp group for any problem with Canvas or WebEx. And session recording will also be there in Canvas. Okay, sir.
Yeah.
Thank you.
Yeah. I will upload the written notes also, but that may not be that much useful because it is just like a scribbling, na? But if somebody wants to see that also, they can see it. Okay.
Yes, that would
But
be helpful. Thank you.
yeah. But this is more informative. I think you can go through it. Except the gates part, I will cover in the next session. Okay.
Okay.
Okay, guys. Bye bye.
Thank
See
you,
you.
sir.